Hello and welcome back to the fourth video in the Swivel Embedding Series. In this video, we'll take a look at block-based matrix sharding for distributed training. In the previous video, we looked at the training objective and the loss functions. But there's still one more problem we need to address. Glove only trains on observed co-occurrences, so the amount of training data is relatively manageable. Swivel, however, explicitly trains on unobserved co-occurrences as well. And since unobserved co-occurrences are much more numerous than observed ones, the amount of training data in Swivel becomes much larger. To train this data efficiently, the authors of the original paper split the PMI and Smoothed PMI matrices into shards and trained them in a distributed manner. So, in this video, we'll look at how block-based matrix sharding works. Let's start with a simple example to see how a PMI matrix is divided into shards. Here we have a small corpus consisting of 3 sentences. First, we count how many times each word appears in the corpus. The word loves appears twice, while likes appears once. Next, we sort the vocabulary in descending order of frequency. Since the appears most frequently, it comes first. When multiple words have the same frequency, we sort them in ascending alphabetical order. This gives us the following vocabulary list. Next, we create the co-occurrence matrix. We place the words along the rows and columns according to their frequency. Then we count how often each pair of words co-occurs and fill in the co-occurrence matrix. The numbers shown in blue represent observed co-occurrences, while the numbers in red represent unobserved co-occurrences. The gray numbers on the diagonal represent a word co-occurring with itself. We set all of these diagonal values to 0. These entries are neither treated as observed nor unobserved co-occurrences. Instead, they are excluded from training. Since the more frequent words are placed toward the beginning of both the rows and columns, the co-occurrence counts tend to be larger in the upper left part of the matrix and smaller toward the lower right. This is what the co-occurrence matrix in Figure 1 of the paper looks like. The bright red pixels represent large co-occurrence counts, while the dark pixels represent small counts. Next, we use this co-occurrence matrix to construct a matrix containing both PMI and smoothed PMI values. For observed co-occurrences, where Xij is greater than 0, we calculate PMI using this formula. Here, Xi star is the sum of the counts in row I, and X star j is the sum of the counts in column j. And d represents the total count. For this example, the xi star vector is shown here, and the x star j vector is shown here. The total count d is 76. For unobserved co-occurrences where Xij is 0, we calculate smooth PMI using this formula. Using these formulas, we get the matrix containing both PMI and smoothed PMI values. The blue numbers represent PMI values, while the red numbers represent smoothed PMI values. Let's calculate the PMI for the word pair bird and loves. Their co-occurrence count is 2, which is greater than 0, so we use the PMI formula. Here D is 76, Xi star is 9, and X star J is 10. This gives us a PMI value of approximately 0.52. Now, let's calculate the value for bird and likes. Their co-occurrence count is 0. So this time we use the smoothed PMI formula. Here D is 76, Xi star is 9, and X star J is 4. This gives us a smoothed PMI value of approximately 0.75. Now that we have these matrices, let's see how we can divide them into multiple shard blocks. Let's bring back the two matrices we created earlier and look at how to split them into the form that will actually be used for distributed training. First, let's take another look at our vocabulary list, which is sorted by frequency. The word the is the most frequent word, so it has index 0. Next comes a, and as the frequency decreases, the words appear later in the list. The vocabulary size, or V, is 9. This ordering is actually very important when we create the shards. For this example, let's set the shard block size K to 3. This means that each shard block will have 3 words along its rows and 3 words along its columns, so each block will be a 3 by 3 matrix. Since our vocabulary contains 9 words in total, we need to split those 9 words into 3 groups of 3 words. So we'll divide the vocabulary into 3 groups as follows. In this example, we chose V and K so that V is evenly divisible by K. This is not strictly required, but it makes the sharding process simpler and helps keep the shard blocks the same size. If V is not evenly divisible by K, the last group may contain fewer words, or we can use padding to make the blocks the same size. This adds some extra implementation complexity and computation. So when possible, it's convenient to choose V and K so that V is evenly divisible by K. Just as a side note, in the original Swivel paper, the co-occurrence matrix is partitioned into 4096 by 4096 blocks. Since the word and context vocabularies are the same, the overall co-occurrence matrix is square, so using square blocks is a natural choice. Now there's one important detail here. We don't simply take the vocabulary list and split it into consecutive groups of 3. If we did that, the first group would contain mostly high-frequency words, while the later groups would contain mostly low-frequency words. In other words, a block containing only frequent words would have many large co-occurrence counts and much more data to process. On the other hand, a block containing only rare words could be almost empty, because those words rarely co-occur with each other. This would create a serious imbalance in the amount of work assigned to different workers. And that would reduce the efficiency of distributed training. So instead, the Swivel paper uses a strided assignment. In our example, V divided by K is 3, so we select words at intervals of 3. Starting with the, we skip ahead by 3 positions and select cat and then and. These three words make up the first group. Next, we start with A and again move forward by 3 positions. This gives us A, dog, and hates for the second group. We do the same thing for the third group. As a result, we get these 3 groups. This arrangement helps make the total frequency of the words in each group roughly similar. Now we can combine these groups to create 9 smaller submatrices, each with a size of 3 by 3. These small submatrices are called shard blocks. Let's start with the first group. We use the words in the first group for both the rows and the columns. This gives us a 3 by 3 shard block like this. This is our first shard block. The numbers inside the block are the co-occurrence counts for each pair of row and column words. Next, we keep the first group for the rows, but use the second group for the columns. This gives us our second shard block. We continue this process for all combinations of row groups and column groups. Since we have 3 row groups and 3 column groups, we end up with a total of 9 3 by 3 shard blocks. And notice something important about the distribution of the co-occurrence counts. The distribution inside each shard is similar to the distribution in the original matrix. In the full co-occurrence matrix, larger counts tend to appear toward the upper left, while smaller counts tend to appear toward the lower right. After sharding, we still have a similar pattern within each block. This means that each shard becomes a relatively self-contained piece of the original matrix, with a more balanced amount of useful data. And this is important for efficient distributed training. Figure 1 in the paper illustrates this distribution of co-occurrence counts in the full matrix and in the individual shard blocks. On the left, we have the full co-occurrence matrix, and on the right, we can see the multiple shard blocks. The same procedure is applied to the PMI and Smoothed PMI matrix. They are also divided into 9 3 by 3 shard blocks using exactly the same row and column grouping. These shard blocks are then used as the training data for the Swivel model. We can distribute the shard blocks across multiple machines and train them in parallel. Or on a single machine, we can assign different shard blocks to multiple worker threads. We'll take a closer look at this when we implement the Swivel model in the next video. So in this video, we looked at how to create shard blocks for distributed processing. In the next video, we'll build a simple Swivel model from scratch using Keras. Thanks for watching, and I'll see you in the next video.